Okay, welcome everybody to this year's OrcaFlex user group meetings for the 11.4 release. My name's David Heffernan. I'm in charge of software development at Orkina, and with me today, James Carlisle, Chris Heaton, Colin Lewis, James Pell. They'll be lurking in the webinar, helping out with any questions that you have. Between us, we're the developers that have been working on OrcaFlex in the last year. So hopefully between us, we'll be able to answer any questions that you have. Now, for this webinar, we're going to cover the new features released in version 11.4, which came out a few weeks ago towards the end of November. All eligible users should by now have received instructions on how to upgrade. I know that quite a few of you are using it based on the feedback we're seeing in our support channels. This is the content what we'll cover today. We might have to skip a couple of the items due to a shortage of time, but I at least wanted to list all these items, and even if we don't cover everything, there's a little checklist for you to pick up yourselves. If there's something that is of interest that we don't manage to cover, you can at least go and find out about it in our documentation in the help file. And even if you don't have 11.4 already, our documentation is available online, so you can access it from our website. We'll be covering new developments in OrcaFlex today, but as always with a new release, we have a new version of OrcaWave. Also, the new features introduced in 11.4 for OrcaWave will be presented in webinars on Thursday at the same times as today. If you haven't signed up but are interested, you still can do. The OrcaWave webinar will include a couple of OrcaFlex developments also, which we're including in that presentation simply because they're sort of very tightly coupled with the OrcaWave developments, and we felt it made sense to do so. As I say, we've got question and answer facility as part of the Zoom webinar package. If you have any questions as we're going along, please do post them in that Q&A. My colleagues will work out what to do with them. Sometimes we'll be able to answer them directly with in the Q&A. Sometimes the answers are too complex to give in a text box, or we may feel that it's beneficial to deal with them live at the end. So if you don't get an answer immediately, just hang on to the end, and you should find your questions answered. Okay, I will move on now to the body of the presentation, and I'll start off as I always do by pointing out the help menu, what's new. This is where you can find out the new features introduced in this version of OrcaFlex, and indeed you can find all the historical new features. But the relevance really is when you get a new version, go to what's new, and any features that are of interest you want to learn more about, follow one of the hyperlinks. We'll take you there to more information. Now I'm going to start off by talking about some changes to the way we handle line seabed contact. And we've been, in recent releases, making a number of improvements in the area of line seabed interaction, and we have more work planned, in fact. So in future releases after this one, we're hoping to bring in functionality to support modeling of upheaval buckling and potential improvements for lines that enter the seabed, let's say close to vertically, like pile structures, conductors, etc. But for version 11.4, we've extended the seabed data on the line form to allow for line seabed contact properties which vary with arc length and or vary between lines. So I'm going to bring up one of my example models and show off how this works. So the data that you can specify differently now is data that has existed before and still does exist in different places, but is now available on the line form as well. And I'll explain how it's interpreted. But looking at the normal and shear seabed stiffness, and we're also looking at line type, lateral and axial friction coefficients. Now, previously, these, as we can see, you'll be familiar with these being specified on either the environment data form or the line type data form. This data can now additionally be specified on the line form, on the seabed page. And this data, this page and data is not entirely new. So in previous releases, we had the ability to specify tangential resistance profiles. What's new is these columns here, the seabed stiffnesses and the friction coefficients. And you can specify these data for specific arc length ranges. So if I wanted to say, different values, for a different range of arc lengths, I can do that here. And the way this is interpreted is if you don't specify the data here, then the value will be taken from elsewhere. So either the environment form or the line type data. And if you specify NA, then again, we will take it from elsewhere for the friction coefficients, the line type data. But here what we've done is we said that for arc lengths between 400 and 600, this line is to have a seabed stiffness of 1. And every other piece of data is not specified and will just pick up the values from elsewhere in the program. So what we're doing here is we're saying that for particular specific ranges, we're overriding that data with the value specified here. A couple more things before I sort of show how the example works. I'm just going to mention that these two data items are the shear stiffness. Now on the environment data, that is just one value. On the line data, we can now specify different values for lateral and axial. This is something that, because the environment data applies to all objects and other objects can come into contact with the seabed, for instance, 60 buoys, and those other objects don't have well-defined lateral axial directions. Lines do have that distinction between lateral and axial. So we're allowing you to specify different shear stiffnesses for lines on this section of the data. That was a specific feature request from a number of clients, in fact. The other thing I would say is some of these data items, if you see on the hint that pops up, it says that tilde is allowed, so I can enter tilde in there if I wish. What does that mean? Well, you come along to the help file. I've just pressed F1 there to bring up the context-sensitive help. And for each specific data item, the help will tell you what tilde means. I won't spend time explaining what's already in the documentation. Now, what we have here is, if we remember, let's have a look back at the environment data form. The overall model-wide seabed stiffness is 25. And for the line, for arc lengths between 400 and 600, we're going to have a seabed stiffness of 1. Those are very low values in SI units at least. And the reason I've used these very, very low values is I want to be able to see on the 3D view, obviously, and clearly what's happening. And so for this range of arc lengths between 400 and 600, the seabed is much less stiff. So we'd expect the line to sink into it more than the rest outside that specified range. If I calculate statics, then we can see exactly that. So yeah, this section here is between 400 and 600 arc length. Now, I also mentioned that it was possible to do this on a line-by-line basis. My example here is a vessel with 12 mooring lines grouped in four groups of three moorings each. I've called them north, south, east, and west. And the seabed stiffness is 275, and I'm going to look first of all at one of the east legs, and it overrides tilde to tilde, and when we have from as tilde, that's the beginning of the line, and when 2 is tilde, that's the end of the line. So this is saying for the entire line, I want the normal seabed stiffness to replace the environment value, and instead use a value of 250 and leave everything else as specified elsewhere. And the other two east mooring lines have the same value. Moving on to the south mooring line has a different seabed stiffness value. The west legs have that same seabed stiffness value of 490, and finally north, they all are 180. So here is a very kind of simple way to see how you specify line by line seabed properties. Now, as I mentioned, I think that's all I'm going to say about this feature right now. As I mentioned, we are working on upheaval buckling and potentially other developments. If this is something that you have a particular interest in, we'd be interested to hear from you. Maybe you've got some opinions on as to how we might do that. We actually have a specification for upheaval buckling and are about to get started on implementing it. But we recognize that user feedback is often valuable. So if there's things you want to suggest to us and contribute, then please get in touch. While we're looking at lines, I'm just going to talk now about shear 7. And we have this with OrcaFlex. If anyone is unaware, the shear 7 VIV program we have a link with OrcaFlex that allows you to generate the input data files for shear 7, to run shear 7 so automatically from within OrcaFlex and read out output files, including drag amplification values, and modify the drag values in OrcaFlex with the drag amplification predicted by shear 7. And actually produce coupled VIV solutions. Now, that's not new. That's been in the program for a long time. But when so in the last few months, there's been a new release of shear 7 version 4.12, and whenever that happens, we have to update OrcaFlex to be able to support it and work with it. And you can see that here there's a new checkbox, or not checkbox, a radio button that allows you to say, I'm wanting to work with shear 7 4.12. This was added actually added in 11.3G, which is the final minor update to 11.3, which we released also in November, and it's also obviously available in 11.4. So if you're wanting to use shear 7 4.12, then you need one of those versions. In terms of impact on OrcaFlex, the changes with 4.12 were relatively small. I think the only change of note is that this this input option. I'm actually not even got my this input option here was formerly only for the stress time history, but now allows you just to capture displacement time histories. The other change relating to shear 7 is in the coupling method, we've introduced a new option. Coupling method allows you to have OrcaFlex statics feeding into shear 7, calculating drag amplification, bringing that back into OrcaFlex, and sort of iterating backwards and forwards until a coupled solution is found. That can take a significant period of time. And if you've already done that analysis and you're then maybe doing sort of further analysis where you're only interested in maybe you're only interested in the drag amplification for interference results, say, it can be frustrating to have to go and repeat that analysis. And as I say, it can be quite time consuming. So what you can do in 4.12 is if you've already calculated the drag amplification, you can say, I want the coupling mode to be user-specified drag amplification. You can specify what that drag amplification is by providing a previously calculated plot file. The plot file is a file that contains the drag amplification. And then OrcaFlex, instead of doing the coupled shear 7 analysis, will sort of skip the shear 7 analysis. It knows you've already done that, and this was the output of interest. And all it will do is we'll read that file, modify the drag coefficients, and do the static analysis without that coupling. So if I just switch back to show the coupled analysis and run that, you see progress, coupling iterations. You see the progress bar running up here in the OrcaFlex status bar. That's generating modes files. This was quite quick because it's a very simple model. But in a complex model, this can take many minutes. Alternatively, if you've already done the analysis and got the drag amplification, we can do statics pretty much instantly because we're not doing the coupling iterations. And here we can see this is the drag coefficient, and these are the amplified drag coefficients as specified in that shear 7 PLT file. Okay, now I'm going to talk about constraints. And I wanted to, when I was sort of preparing this presentation, I wanted to cover some of the history there because it's relevant. And I discovered that constraints were actually added in version 10.1, which was 7 years ago. I can't quite believe it was that long ago, given I still think of constraints as a recent feature, as a modern feature, which I suspect shows that I'm not very modern when it comes to working with OrcaFlex, sadly. Back then, that immense time ago, 7 years ago, when we were developing constraints, we actually considered different options for implementing them. There are actually different ways to implement them, and they're quite different ways. And the two main candidates that we considered were a method based on coordinate mappings and a method based on Lagrange multipliers. And we ended up opting for the method based on coordinate mappings. There's various reasons for that. There are actually pros and cons to both methods, and at the time, it made sense for us to go with the direct the coordinate mapping method. Now, over the years, we have encountered situations where the Lagrange multiplier method would have been more effective. And recently we decided to go ahead and implement that. And we've done that. It's not to replace the previous method. It is in addition to. So now you are asked to choose between these two solution methods. Direct is the coordinate mapping method. Indirect is the new Lagrange multiplier based method. And when you choose to use indirect, you also have the option of what's called a double-sided constraint. And I'll talk about those a little bit later. When you are using indirect, the indirect method, then to implement the Lagrange multipliers, we have to introduce additional non-physical degrees of freedom into the model. And you might, well, one of the consequences of that is that indirect constraints are not compatible with the explicit solver. Hopefully that's not going to affect too many people because, you know, mostly you'll be using implicit and time domain analysis because it's usually much faster. But indirect constraints are also not compatible with modal analysis. So that, as I say, there's like some pros and cons, and this will be, you know, these will have been some of the reasons why we ended up going for direct coordinate-based mapping approach initially. So as I say, with the direct method, you have these additional degrees of freedom to represent the Lagrange multipliers. Now, you might imagine with additional degrees of freedom, that's going to lead to larger system matrices, slower performance. But it turns out that there's often offsetting gains to be had because with the direct method and the coordinate mappings, it can take significant time transferring loads in Jacobian terms, especially if there's a chain of constraints connected together. Usually, the performance of the two methods is pretty similar. I mean, usually constraints aren't going to be the bottleneck in your model, but some systems that are using a lot of constraints, they can actually become the bottleneck, particularly when you have long chains of constraints. And in those situations, the direct method can actually become quite slow, and indirect can be a significant performance benefit. So I'm just going to show one such case and also use it as a way to look at some of the trade-offs and benefits of indirect. So here I'm going to bring up this is a solar panel array model. And these models actually are one of the types of models that have been motivating us to work with indirect constraints because they can be quite tricky with direct constraints. And if I look at this model, well, I've got, just close everything up. We've got our panels, 4 times 8, that is 32, I guess. And then we have the constraints. The columns are fairly, well, the columns should be fairly straightforward. Let's zoom in, and I'm actually going to show this first column. The columns should be fairly straightforward. We should just be able to connect them with just with constraints. But because of the limitations with not being able to have loops and a circularity in our connection relationships, we end up having to use these kind of annoying single segment line connectors. And that's a sort of feature of this model. We see the same thing in the rows. You might want to just have constraints, but actually we end up with these do nothing connector lines. And if I switch back to types mode, you know, we've got, you know, a handful of mooring lines and then pages of these single segment connector lines. It's tricky to build a model. It's also turned out to be a little bit slow. I won't dig into explaining the connectivity in this model because it's so annoying with all these connector lines. Before I move on to the indirect, which will be a lot simpler, I'll just bring up the properties and note that this simulation took 207 seconds to run. Now I have a similar model of effectively the same system, modeled slightly differently using indirect constraints. And before I go any further, while the figure of 207 is fresh in the memory, this model took 35 seconds to run. So nearly 10 times faster, which is, you know, quite a significant speed up. And if you were to use a solar array that was bigger, that performance difference would sort of spiral and spiral. So this is really, really useful for these very specific cases. I'm not trying to say this is going to benefit all systems. Now, actually, let's just go back to the tabs. One of the nice things we see immediately in the indirect version, we haven't got a single connector line. We don't need them anymore. And if I look at our constraints, these are all the constraints in this model are double-sided constraints. I'm going to show the columns, and they are they have a single rotational degree of freedom, completely free to rotate about x. So x is that axis on the screen, center of the screen there, and this is just a simple hinge. And you'll notice that, previously with a single-sided connections, you would specify, panel 1 connected to constraint 1. Then on the constraint data form, you'd specify constraint 1 connected to panel 2. Then back to panel 2 data form, you'd specify, again, the connection is to this other object. Whereas one of the nice things here is that I can leave my panels all completely free and just define this constraint is between these two panels. And then the next one is between the next two panels. Double-sided connections give you, in many ways, it's the nicest thing about them is the ease of model building, ease of understanding your model. The other benefit, though, is that we avoid all of the limitations of sort of circular connections. So it turns out that we can have pretty much arbitrary chains of connections here within reason. It has to be something that's physically plausible. If it's not physically plausible, then your system won't solve. If I move on to the rows, because they are really quite interesting, with another benefit of double-sided connections. Just hide all of these, and I'm going to show row 1. Again, these are all double-sided connections. Again, the benefit of seeing both the objects which we're connecting in one place. All degrees of freedom are free, so it's a very different kind of connection. But what we have instead of a rigid connection is we just have a translational stiffness. And this is meant to sort of represent some kind of mesh or membrane kind of connection, kind of thing that allows you sort of an articulation. If I look through the replay, you can see what happens as the panels are moved by the wave. They're all articulating with respect to each other. So a different type of connection. Let's just look at what's connected to what. So here, the first, well, if I look at these two here, between panel 1 and panel 2 in row 1, and this constraint joins panel 1, panel 2 of row 1, and the next constraint joins the same two panels. So I've now got two objects connected together with two different constraints, which again is something you couldn't do with direct constraints. So a lot more flexibility with indirect constraints. I'm going to leave it there in terms of the technical side. I just want to mention, refer you to the documentation. We have a new topic called constraint solution method. A lot of very useful information to be had in here, but in particular, I said earlier on there were pros and cons to both methods. Well, the pros and cons are sort of explicitly called out here for direct and then indirect. And one of the sort of beauties here, I would say, is that by having both available, you will use both, and you will sometimes use both in the same model, simply because you want one benefit for one use and a different benefit for a different use. So it's not going to be, we're always going to use indirect from now on. You will continue using the direct. Each has its place at certain times. Now, one of the sort of consequences and side effects of double-sided connections, it turns out, is that it's much more common, or quite easy, shall I say. It's quite easy for you when using double-sided connections. It's quite easy to encounter systems which are indeterminate. So the extra flexibility of the connectivity and the use of Lagrange multipliers just does mean that sometimes it's possible to build systems that are indeterminate, for which there are maybe multiple solutions. And when we have these non-physical degrees of freedom, you can have multiple solutions that are all physically equivalent, but you maybe have differences in the Lagrange multiplier degrees of freedom. So once you have an indeterminate system, and if you're familiar with OrcaFlex, you'll be used to seeing, when you run static, sometimes you see this error message where you have an indeterminate case, which has been sort of diagnosed by the Jacobian being singular. Why is that the case here? I'm going to illustrate this particular feature without using constraints, but it was kind of motivated to make the double-sided connections work well. And why it happens is, here I've got a 60 by a point mass. The mass is at the origin, and the link, which is a simple spring, is also connected at the origin. So what that means basically is that the 60 by its rotation is completely arbitrary from the point of view of finding a spherical equilibrium. It doesn't change the outer balance loads. So any orientation is a solution to the problem, which is an underspecified or an indeterminate system. So that's why you get that error message. And I'm sure all of the users will have encountered this from time to time. Usually there's techniques to solve it. You see, oh, okay, I need to, well, in this case, I would simply say, right, let's only include the translational degrees of freedom in statics. There's different variants of this problem that you solve in different ways, but usually there's a physical way to solve it. For when you encounter this problem due to use of indirect constraints, though, often there isn't a physical solution. And we spent quite a bit of time grappling with this when we were developing the feature. It was quite challenging. We eventually came up with a solution that isn't grounded in some great, wonderful piece of mathematics. It was very much a sort of pragmatic approach. And what we found was that if you perturb the Jacobian by a small amount, and we actually just add a very small value to the to each diagonal entry in the Jacobian. If you do that, then that is often sufficient to allow the problem to be not singular, allow you to get to your solution. And so long as that perturbation is small enough, then and you're satisfied that you've not affected the accuracy of the solution, then that's often a very pragmatic way to solve this problem. So we've gone back to the situation where we have a singular Jacobian. If I show how you avoid that using the new functionality, it's on the Jacobian page, Jacobian perturbation factor. We put in a small value, and now statics converges. So I don't recommend you habitually putting a non-zero value in there. Only do it if you need to, which is why we've left the default at 0. And if you are going to do it, then you definitely should come and read the documentation, because the documentation talks about the impact of of perturbing the Jacobian and effectively making the Jacobian incorrect. In summary, for statics and implicit time domain dynamics, Jacobian is used really just to guide convergence. So if you converge, you're going to have a valid solution. For explicit time domain, then it doesn't apply at all. Well, with a proviso on the recommended time step here, but again, I don't think explicit is very relevant these days. And for frequency domain and modal analysis, actually the Jacobian does impact on the results. So here you do need to be careful, particularly careful to make sure that your perturbation is small enough not to have a significant impact on the results, which I guess you can test with sensitivity analysis. So I just want to put out a big warning. Don't go and use this without being confident you know what you're doing and having checked the documentation first, particularly these scary warnings in red. Right, we're going to move on and talk about features to do with environment next. And the next thing I want to talk about is tabular current. So the current specification that's offered within OrcaFlex now has been expanded quite significantly. The previous way of specifying current is still available. It's under what's referred to as the variation scheme current model. All of this still exists, and you can carry on using it. The new option is called tabular current, and tabular current allows you to specify a field, a velocity and acceleration fluid kinematic field that is time varying. See in my data, the time column is varying, and you can specify velocity acceleration at a series of points. So there's a spatial grid as well, and OrcaFlex will interpolate in this sort of 4D space of time and position. And you must have a complete grid, so every sort of combination of positions and time must be present in your data, and OrcaFlex will take this sort of flat data structure that you're expected to provide and work out how that is as a grid and then do interpolation. And it's very similar to how things are done in other places in the program, like in CSET REOs and QTFs, tabular line contents, and so on. We've called this current, but in principle, you could use it for things that weren't current. You could have a full wave field here, potentially. This is the only place in the current modeling of features of OrcaFlex where you can have an acceleration, which then feeds into loading the acceleration terms in the Morrison loading, like sort of inertia terms. The other, even if you had a time varying current or a ramped current, that technically does have an acceleration. In other words, the velocity is not constant at a particular point, but we don't actually account for that in OrcaFlex. For tabular current, we do account for that. The file can be either internal or external. I think a lot of times people gravitate towards internal because you just keep all your model data in one file, and that has its benefits. However, this data can be absolutely huge, and if it gets really huge, then the GUI can become slow to work with, and also you can end up with the same data duplicated into lots of files, and you can have storage issues. So there's an option to put the data in an external file in the same format, tab delimited. Actually, it might just be tab or space delimited. I suspect it's tab or space delimited. Anyway, the documentation will explain how it is. You can check that it's interpreted correctly anyway by the preview button. You make sure that these values correspond to what you expect them to be. I'm going to just run the dynamics, and now we see the this drawing up here? Well, this is the other kind of half of the feature, which is that you can now visualize tabular current. Because it's so much more complex than the other current models, we felt it was important to be able to kind of see whether your data matched what you expected it to be. And on the drawing page, you can decide whether to draw velocity, acceleration. I'm just going to leave it on acceleration, run the replay to see. This is actually sort of a potential theory solution for flow around a cylinder which is moving. At least the person who developed the model told me that's what it is. So I hope that's correct. The arrows, the direction of the arrow is the direction of the current, and the color indicates sort of the speed of the current. Okay, let's talk about wind, which is the other change in the environment data. And I'm going to first of all talk about Mann wind. And the changes with wind have been motivated by our wind turbine modeling. So the wind turbine modeling, there's a standard IEC 61400-1, and it recommends for design loads for turbines two wind turbulence models. Sorry, these are the Keimal and the Mann models. Previously with OrcaFlex, if you were using wind and you're using full field wind, which is what we're talking about here, then the only option we had was TurbSim. And what we do there is you do a TurbSim analysis, which is an NREL tool, and that produces an output file, a BTS file, and you can import it in this field here. The thing is, though, TurbSim supports the Keimal turbulence model. It doesn't support the Mann model. So we have quite a few users that have been asking about this and wanting to use Mann turbulence model. We've even had users that have been taking Mann turbulence data and then sort of converting it to the TurbSim BTS file format, which is not a task for the faint-hearted. So to make life easier, we've added the option to directly import Mann wind, and this is invariably generated by a tool from DTU called it's the Mann turbulence generator. Unlike, it's a bit more complicated in terms of all the inputs that you needed from the OrcaFlex side. With TurbSim, you basically provide the file, and the file comes with a header that has a lot of extra description. With Mann, that information isn't contained in the files that are generated, so you have to input them yourself, which is, what you can see here and down here. And also, there's not even just a single file. You actually get three files for UV and W, which are the wind velocity component in the X direction, the Y direction, and the Z direction, respectively. You also have to specify the grid data, so the number of grid points in the X direction and the Y and the Z direction. Not only do you have to get these such that the total number of points, i.e. nx times ny times nz, corresponds to the size of these files, which OrcaFlex is able to check. You need to get them in the right order. So if you sort of transpose these values, then you can be in all sorts of trouble. Similarly, the separation, spatial separation, again, it's up to you to get this right, and you have to, again, make sure that you don't transpose them. You also specify the mean speed, which determines the sort of rate of propagation, amongst other things. So if I look at this, you can see the wind propagating 14 meters a second. If I zoom out, there's actually an infinite number of boxes. That's because with Mann wind, it's assumed to be periodic. I'm also going to show that we haven't left out sort of drawing for wind. So this is a little bit similar to the current drawing we just saw, where arrows are used to represent the fluid, the wind velocity, again direction by where the arrow points, and then color indicating wind speed. By default, you get a single slice at the origin, but you can choose to have multiple slices. You can change the scale, which basically affects the color and the length of the arrows. So tilde means use the mean wind speed. So if I put in a value of 14, shouldn't change anything because that is the true mean wind speed. Then if I change the value, you can customize how this works out. I'm going to go with a value of 12. Also visible in shaded view. The two final things I wanted to mention to do with Mann wind. There is also vertical variation factor can be applied, and there's also target standard deviation that can be used to scale the dynamic part of the wind. I'm not going to explain that in any more detail and just refer you to the documentation. Now, one of the things when we were working with this development and the other development with wind is we realized that ramping for wind was a little bit ad hoc previously. So different wind types had different options for ramping. Some of them didn't have any options at all for ramping, and ramping was handled on a sort of wind type by wind type method. But what we've decided to do is we've decided to unify everything and provide a single unified way of handling ramping and specifying what ramping you want done with the wind. I'm going to demonstrate this for Mann simply because it has some nice visualization, but this ramping box that I've highlighted on screen, this applies to all wind types. Now, unramped is what we have at the moment, and if I calculate statics, then we see we're now at the end of statics. I'm just about to do dynamics. We've got no ramping, so we have the fully dynamic wind at the time where statics is assumed to take place. Let's have a look at ramping from mean, and if I do statics, now we see this represents 14 meters per second, which is our mean wind speed. If I run the analysis, and then sort of step through the replay, we see we gradually ramp up the dynamic part on top of our mean. And then finally, keep doing that. There we go. Ramp from 0. Nothing in statics because it's 0. And we go back to statics and we start moving through the simulation, and this is very small wind speeds. So gradually, as we go through the build up, gradually get up to this fully developed dynamic wind. And as I said, it's important to stress, I've demonstrated this for Mann, but this applies to any wind type. Okay, that's a unified way of handling ramping. The other change with wind, also motivated by turbines, is we have a new extended time history method. So previously, time history of speed or time history of speed and direction. Now we have this time history of speed, direction, shear, and gust. This again comes about through the IEC standard. There's a bunch of design cases in that standard. The extreme wind shear, EWS, extreme operating gust, EOG, and extreme coherent gust with direction change, ECD. All of those cases actually were extremely hard to model previously in OrcaFlex. I think realistically the only way you could do it was to sort of fake a BTS file for a full field wind that gave you what you wanted. So that was a real limitation. But all of those design cases from IEC 61400-1, they can now be handled very easily using this new extended time history wind type. Let's have a look at turbines themselves. A couple of changes to do with turbines. First of all, I'm going to look at rotation sense. Now, generally, most turbines, offshore turbines, are upwind, so the rotor is upwind of the tower. And again, generally, these turbines, they will rotate clockwise when viewed from upwind. It's not 100% so, I'm led to believe, but that's the most common way things are done. But it's also sometimes the case that we use, or people use downwind turbines or turbines that rotate anti-clockwise. And you've actually always been able to model these in OrcaFlex. The problem is it's very hard to put the data in correctly, because the way we've designed the data inputs are make sense. It's easy to put the data in for a clockwise rotating turbine, but if you have that data and you want your turbine to be rotating anti-clockwise, then it turns out you have to change a lot of the data, you have to mirror a lot of the data. And that process is complicated and error prone. So what we have now is the ability to specify the rotation sense. And that really tells OrcaFlex how to interpret your data. And in this particular model, we have turbine that's clockwise and this other turbine that's anti-clockwise. These are cut down versions of the K01 example. If I compare the data for the two turbines, we see the names different, the connection to the nacelles different, the positions different. Well, not really different. The rotation sense is different clockwise for one, anti-clockwise for the other. So that's the main change. And then the tower positions are also different. But the rest of the data, all the sort of structural profile data, blade profile, all that kind of stuff is unchanged. If I now load the sim file, have the replay run, we can see that the two turbines rotate in opposite directions. One on the left is clockwise, the other one is anti-clockwise. However, the results, one from each of the two turbines, are identical. So this feature doesn't give you anything that you couldn't already do. It just makes it a darn sight easier with a simple flick of the switch. Also, a little bit related, when we're talking specifically about downwind turbines as opposed to anti-clockwise turbines, although they're often the same thing. But when your rotor is downwind of the tower, there's an extra aerodynamic effect that's important, which is called tower shadow. So there's a velocity wake deficit. If the wind's coming, hits the tower, has to sort of go around the tower, and that influences significantly the aerodynamic field seen by the blades. And there's a couple of standard methods widely used in the industry to model this effect. This effect's called tower shadow. So 11.4 has this new data item. It goes on the tower page. It shares sort of tower connection and tower profile data with tower influence, which is the pre-existing data. But for tower shadow, you get to choose between, well, maybe you have no tower shadow, or you use one of these two models, Powell's or Eames. They have slightly different data that needs to be specified because the model is slightly different. I think the overall the models are sort of similar behavior. There's not, as I understand it, or as I've been told, not too much. Particularly to prefer one or the other, but we've added them both because it was fairly routine to do so, and they're both in use. I'm just going to demonstrate again. I've got my simulation. You'll notice this little red shape. That's this tip shape, and that's connected. That's connected to drawn in red, as you see there, connected to the turbine, blade 1, at end B of that turbine. So it's connected to the tip of blade 1. And it's really just a sort of visual indicator, so you can see when the replay is running. 2 graphs, undisturbed relative velocity at that same point on the blade, the NB of blade 1 at the top. So it's just a constant wind speed in this particular model. However, the disturbed relative velocity, where the tower shadow comes into play, we see when the blade passes behind the tower, the wind velocity drops because of the presence of the tower. Okay, we're getting near the end, honest. I want to talk about a feature that's been removed from the program and explain a little bit why we've done it. And I'm going to show you a screenshot from version 11.3. This data, simulation time origin on the environment form on the waves page, and simulation time origin no longer exists. Here's 11.4, the same page, and simulation time origin is gone. And why have we done that? Well, here's the excerpt from the documentation for 11.3, and simulation time origin documented and described here. It's given in terms of global time. So back in 11.3, we had the concept of global time and the concept of simulation time, and we then had other things like wave train or time histories had their own time origins. So we had lots of different concepts of time. One of the things that simulation time origin allowed you to do was to shift everything all in one go. So that that was why it existed. It didn't exist for no good reason. It existed to allow you to shift time all in one go. However, what we've found over many, many years is we all struggle to understand global time, simulation time, and on all the other time systems in OrcaFlex. And we've also always struggled to explain it. Whenever we do training courses, we've found this a very complicated and tricky thing to do. This graph itself is I find frightening. If we look at the modern day 11.4 version, we see the same figure. Simplified now, there's no global time anymore. So wave train time and time history, those origins are now specified with respect to simulation time. So that has simplified it, by removing coalescing global time and simulation time into one thing. However, how do we shift everything in one go? So you typically end up doing that if you're doing maybe you're looking for. I mean, one of the common ways when you do that is when you're looking for a specific wave with certain properties, and I'm just going to demonstrate doing that. Here I've got a wave search. I'm looking for waves with steepness greater than 0.17, and I'm looking within a 10,000 second window. And we found 3 of these waves. And the one I'm going to focus on is here. It's a fall at time 4617. And it's got this particular steepness. It's the largest steepness of the 3 that have been identified. So just remember that time, 4617. Now, previously, we might have come to the wave page. Were simulation time origins still there, we might have shifted time accordingly, so we could have our simulation just focus in on a small window around that particular point of interest. We could alternatively use the wave time origin to shift it. But if you have multiple wave trains, or you have wave and wind and time history, then you'd have to shift them all potentially. So what we've realized is that there's another way to do this, which is we can shift the time by changing which simulation times we simulate. So actually, we're not really shifting time. We're just saying, I'm going to just simulate just a window specifically on this time. So we wanted 4617. So I'm going to go for 200 second simulation. I'm going to have the first stage numbered 1, just because I can. I'm going to have a 20-second ramp. So we're going to have a simulation time between 4500 and 4700. So we're going to capture our 4617 time. I run the simulation, put my graphs. Now we see this is the entire simulation, but it's just the point of interest that we highlighted earlier. And yeah, this is 4617, and this is the very steep fall that it talked about. So we kind of felt that given that there was this way of achieving the same effect using the analysis data, we just wanted to simplify the whole handling of time. I've got a very small number of things that I will just mention very, very briefly. I can probably do this in 2 or 3 minutes. We have some new results variables. I'm going to demo them for lines. And previously, velocity and acceleration available relative to Earth with respect to global. There are new local variables relative to Earth, but with respect to local axes, in this case, node axes. I've shown them for lines, but they're also available for 60 buoys, turbines, turbine blade nodes, vessels, constraint in frames and out frames. A useful little feature here to do with, again, to do with lines. Here I have some attachments. I'm connecting these attachments at nominated arc lengths. My line, though, is 100 meters long. It has 10-meter segments, so it has nodes every 10 meters. And the clumps in this data will be connected at the nearest node to the specified arc length. So although I've asked for the clump to be at arc length 13, there isn't a node at arc length 13, and it goes to the closest node. We've added this new column of data to tell you what the arc length of that closest node is. And in this case, the closest node to arc length 13 is 10. The other one is maybe a little bit more interesting. 25 meters from end B is an arc length of 75. There are nodes at 70 and 80, so we're exactly halfway between. So you might well ask, where do we go? Is it 70? Is it 80? This new data tells you. We've added the same for applied loads column here, midline connections. You can also access this information from the API. There's a new API function to do that. Restart. Actually, it's easiest just. I'm just going to show the data. The original versions of OrcaFlex that handled restart, you had to restart from the end of the parent simulation. In 11.3, we allowed you to restart from points within a simulation. We call that mid-simulation restarts. But those mid-simulation restarts could only take place if something called restart state had been recorded at specific points in the parent model. And you have to nominate those points where the restart state is stored. In 11.3, you have to nominate those times ahead of time. The reason we ask you to do that is I know it's inconvenient, but the alternative is you do it every single possible time. If you do that, your simulation files become absolutely humongous, huge. So you need to be able to say, I don't want to do it every single time. Sometimes, though, you want to restart from a particular specific event in the parent. And that's what this restart state recording test allows you to do. Here you can enter some Python code. OrcaFlex will call that Python code every candidate time sample where a restart state can be recorded, and you can query the model. In this case, in the documentation, we have an example where we ask for effective tension for each of the mooring lines in the model, and if it's bigger than 90, then we will record the restart state and allow that mid-simulation restart to happen. So this gives you the sort of flexibility to not have your simulation file sizes balloon, but also make sure that you have restart state captured at a specific point of interest. And the very final thing I want to go over is Bitmap Canvas API, which is an API feature. And this really came about from a number of feature requests over the last year from a bunch of users all suffering from the same problem. And these are typically, it was installation analyses where you have a snapshot of different steps in an installation process. Sometimes it's like each step is a different model, or maybe it's a number of models, but maybe within some models there's different times. And what is hard to do is to get a single image representing all of those steps in one image. So we have facilities in the API for generating images, 3D view images, but it was really basically impossible to superimpose them. The reason being you couldn't deal with the background. You kept overwriting what you had before. It was not possible to get a transparent background. So we've added the Bitmap Canvas API in 11.4 that allows you to do that. I'm just going to run this. So this particular script, it loads up two different simulation files. It draws onto the canvas here, which is held in a Python context handler using with. It draws the parent at the end of the simulation, and then it draws in the restart at these simulation times. It draws on top of that onto one image. And if I run this, we'll see the image file will appear, generated through the API. And yeah, this is capturing a whole range of different snapshots all in one image. Okay, I know I've overrun. There was quite a lot of content to get through. I'm going to say nothing more about my presentation. If anyone's got any more questions to ask, now's the time to do it, and we can answer them now. If you're not interested in seeing any of the questions, then fine. You're free to leave. I would say though, in the next day, you'll receive an email, post-webinar email, inviting feedback. That feedback's very valuable to us, so we would appreciate receiving that. If you're attending the OrcaWave webinar as well as the OrcaFlex webinar, then it's best just to send the feedback once only. So wait until after you've had the second OrcaWave webinar on Thursday. Recordings of the webinars will be published on our website in a few weeks' time. But in the meantime, you will be able to watch these webinars as on-demand webinars. You go to the same sign-up link. Well, I mean, you won't want to watch it because you've just watched it, right? But maybe if some of your colleagues couldn't make it or you think might be interested, you can go back to the same place you signed up for the webinar, and if you sign up again, you will actually watch the webinar on demand. And yeah, I'll just try and look at the last few questions. So the question, if you change the coupling to consider VIV drag amplification factors, is it also considered during the dynamic analysis? Yes, it is. So the drag amplification is carried through to dynamics. That's exactly the same as it is for the coupled VIV at the moment. So it's handled exactly the same way, I believe. Will you provide Python example using Bitmap API, capturing multiple snapshots and multiple files? I think there's one in the documentation. So I think that's already covered. So yeah, look in the API documentation, we have an example for that. Think everything is answered. If anyone has any more questions they'd like to ask, now's your chance. But I suspect that's probably it. Thank you all for attending. I think over the course of the two webinars today, because we did them for different time zones, we've had around 170, 180 attendees, which I think is really nice to see. Look forward to seeing your feedback in a couple of days or a few days' time, and I look forward to maybe seeing you and hearing from some of you again on Thursday for the OrcaWave presentation. Okay, thank you very much. That's all from us, and we'll see you on Thursday. Bye.